All right, in Chapter 6, Section 3, we're going to start by talking about what a binomial distribution is. All right, so there's some conditions to know if the setting is binomial. So there's 4 questions you ask. The first is it binary? Meaning the possible outcomes of each trial can be classified as success or failure. There's a clear success and a clear failure, and I'll demonstrate that in a moment for you. The second condition is the trials have to be independent. Each trial must be independent, that is, knowing the result of one trial does not tell you anything about the result of another. For instance, if I flip a coin and get heads, that doesn't tell me the next one's going to be heads at all. They are independent of one another. The third question is number. The number of trials N of a chance process must be fixed in advance, like you know you're going to flip a coin 10 times or roll the dice 5 times. There's a very clear number of trials. And then lastly is the same. The probability of a success has to be the same for every single trial. If I flip a coin 10 times, probability of getting a head is the same every single time. It's still 1 out of 2. All right, so those are the 4 things, and we use a acronym BINS. So we just say check the BINS, make sure it's binomial, and then you can proceed with the binomial calculations. All right, so just some definitions. The count X of successes in a binomial setting is called a binomial random variable. A probability distribution of X is a binomial distribution if the parameters of N and P, where N is the number of trials and P is the probability of a success on any one trial. The possible values of X are the whole numbers from 0 to N. Like I flipped 0 heads or 10 heads, or anything in between. But they're whole numbers. That makes it a discrete, but specifically a binomial random variable. Now, most common mistakes students make on these is missing the whole fact that it's a binomial distribution. They don't recognize that it's binomial. They think it's a normal distribution, and they proceed with normal calculations when they need to use binomial calculations. And honestly, it's one of the most commonly missed test items. So make sure you check the BINS every time before you proceed, jump to any conclusions, okay? All right, so let's walk through one of these and see how it goes. Determine whether the random variable below have a binomial distribution and justify your answer. All right, so basically we're checking the BINS. A, roll a fair die 10 times and let X equal the number of 6s. So the first thing I have to check is it binary? Well, in this case, a success is getting a 6. A failure is not getting a 6. So there's a clear success and a clear failure. Then I check for I, for independence. And it is true that one roll of a die does not affect the next roll of the die, so they are independent trials. And N is the number of times I'm doing it. Well, it tells me in the question I'm going to roll a die 10 times, so that's clear. And then S is the probability of rolling a 6 the same every time. Well, yeah, it's 1 out of 6 every time you roll the die. So this meets all 4 criteria, so it is a binomial distribution. Let's try B. Shoot a basketball 20 times from various distances from the court. All right, let Y equal the number of shots made. Well, B is for binary, and a success is that you make the shot. The failure is that the shot is missed. I is, are these shots independent? Well, one shot does not affect the next. That's true. N, how many times am I shooting the ball? Well, it tells me 20 times. And the S is for the same. Is the probability of making a shot the same every time? It is. It's 1 out of 2. You either make it or you don't. All right? So this passes the binomial distribution test also. All right, last one here. Observe the next 100 cars that go by, and let C equal the color. All right, so let's check. Is it binary? Is there a clear success or failure? Well, it says the success is color. Well, what color? Since there are more than one color possible, this is not binary. We don't have a clear distinction of what the success is. If it was a red car, great, that's a success. Anything else is a failure. But because we don't have a clear success, and there's more than one possible answers, this is not a binomial setting. So I've checked BINS, it's not binomial, I can't proceed with this problem. Okay, so let's try one of these actually. In many games involving a die, rolling a 6 is desirable. The probability of rolling a 6 when rolling a fair die is 1 out of 6. If X is the number of 6s in 4 rolls of a die, then X is binomial with a number of trials of 4 and a probability of success of 1 out of 6. All right, so then it asks me, what's the probability that x is 0, meaning I don't get any 6s? That is, what's the probability that in all 4 rolls there are no 6s? All right, so let's map this out. Let's think it through it. It's probability that x equals 0. That means I have 4 fails, no successes. All right. Well, if they're not 6s, if the probability of a 6 is 1 out of 6, the probability of not having a 6 is 5 out of 6. So that probability is 5 out of 6 for each of the 4 rolls. So I could write it this way. And calculate it out, I get 0.482. Okay. But what's the probability that x equals 1? I get 1 6 out of my 4 rolls. Well, that's a little more complicated because, let's say I get the success on the first roll. All right, so it's 1 out of 6 times 5 out of 6 times 5 out of 6 times 5 out of 6. And it looks like this. But do I have to have it on the first roll? No, that success could come on that second roll. I still have 1 success out of 4. But notice that my probability stays the same because I really have 1 success and the rest of the 4 trials are failures. But again, the success could come on that third roll. But again, the outcome is going to be the same. Notice. And then lastly, what about the 4th roll? What if I didn't get a success to the 4th roll? Well, that probability of success comes down here, but the actual answer is going to come out the same. So all these answers come out to be the exact probability. There's just 4 ways to get it. So you have to take into consideration the 4 different ways you could get 1 success out of 4. All right, so I have to multiply this whole probability back here by the 4 combinations that are possible. All right, so that complicates things a little bit. It's not as straightforward as we did up here with 0 successes. When you have 1 success, there's more than one way to get 1 success. So let's look further into this. Okay, so let's think through the other number of successes and look for patterns here, basically. All right, so what about probability that we have 2 successes out of 4? Well, there's 6 ways to get 2 successes, but the probability of a success is to the 2nd power, and then that means I have 2 successes and 2 failures. So it's raised to the 2nd power, and I get 0.116, okay? But there's 6 ways to get it, so I have to multiply by that 6. What about the probability of 3 successes? Well, if you mapped it out, there's 4 ways to get 3 successes. So notice that my probability of success is to the 3rd power, and that means I only have 1 failure to the 1st power. But there's 4 ways to get it, so I have to multiply by that coefficient of 4. And then lastly, probability of 4 successes. There's only one way to get 4 successes. So my probability of success is to the 4th power. Failure is to a 0 power, but remember anything to the 0 power is just 1. So I put this here just so you can see the pattern going on. And I raise it, and it's only one way that you can get it, so I multiply by 1, and I get this probability here, 0.007. So the question becomes, well, how do you know these numbers of combinations over here? These make a little bit of sense, right, to the powers, successes, and failures. But how do you know the combination number? Well, we call that the number of arrangements. We call that the binomial coefficient. All right, and there is a formula for that, and it looks like this. And notice there's no bar, it's not a fraction, but we read this as n choose k. So like in 4 trials, I choose 2 successes. And there's a formula behind this, and it looks like this. It's n factorial over k factorial times n minus k factorial. And I can show you what a factorial is when we get to class, but it's a complicated extra calculation, but we can bypass it with our handy-dandy calculators. I just want you to know that this represents an equation that the calculator is doing for you. Now, it's giving you this coefficient. The rest of this you need to figure out. So how do you find this number? Well, in your calculators, if you hit the math button, you go over to probability, and in option 3, there's a combination, n choose r, right? And when you choose that, you get this in there, and then you'll have to put in how many number of trials. And we had 4 trials, 2 successes. When I hit enter, it gave me 6. That's where that coefficient came from, right there. And I repeated the process for these guys. Now, in general, how do we calculate binomial probabilities? We said on the previous slide, you have to have a coefficient, probability of success, probability of failures. All right, so let's look at the generic equation. It looks like this. If I have k successes, out of n trials, I choose k successes. The probability of a success to the k power, and then 1 minus p is the probability of a failure, and the rest of my trials right here. So it's n minus however many successes I had. All right, And that's what we see right here. If I look back at my equation, let's say for the x equals 2, I had my n choose k, that's what we got in our calculator. Probability of success was 1 out of 6 to the second power, because I wanted 2 successes. Probability of a failure right here. And then n minus k, I had 4 trials minus the 2 successes, leaves me with 2 failures. And the pattern continues with these others. So if you need to pause it and think through it, feel free to do that. Okay, so let's look at this example. In roulette, 18 of the 38 spaces on the wheel are black. Suppose you observe the next 10 spins of a roulette wheel. A, what is the probability that exactly 4 of the spins lands on black? So before I jump into any equations, I need to mentally check through bins. Check through my list. B, what's my clear success, clear failure? My clear success is landing on black. Failure is not black. Okay. I, independent, is each spin independent? Yes, it is. And do I have a clear number of trials? Yes, it says 10 spins. And then probability of a success, the same. Well, 8 out of 38 is the number of black on the wheel. Okay, so bins works. So I need to think through my formula. So here's my formula. If x equals 4, I want 4 successes. Though I have 10 spins, I choose 4, so this is my binomial coefficient. Probability of a success is 18 out of 38. I want 4 of them. Probability of failure is the complement. So 38 out of 38 minus 18 out of 38 gives me 20 out of 38. And then to get this power up here, I take that 10, subtract the 4, and I get 6. So I do all this business in my calculator, and I get this probability. And then I have to interpret that. I'd say there is approximately a 22.5% chance of landing on black 4 times out of 10 spins. So notice I did have to include how many trials I had here. And probability is an approximation. It's not exact. Keep that in mind. All right, let's look at B. What's the probability that at least 8 of the spins lands on black? Well, that could be 8, that could be 9, or that could be all 10, right? So I have to think through this equation 3 ways. I have to do it for 8, for 9, and for 10. So probability of 8, follow your pattern. Trials over successes, success to the number of successes we wanted, probability of success, failure to the rest of them. So if there's 8 successes, that's 2 failures. I get this value. Probability of 9 successes, 10 choose 9. The first probability of a success to the 9th power, the remaining to the failure probability, gives me this probability. And then all 10 are black. Well, 10 out of 10. Here it is, probability of 10. And then to the second, or to the 0 power, because I'd have no failures, gives me this. Now, to finish this, I have to add all 3 of these up, and there's my final answer. Okay? And then typically I would interpret my answer. But I just want to model for you, if it's something like this, this is one way to handle it. And we'll look at other ways in the next video.